Hello. This should be the last clip for the semester, okay? And we're gonna try to wrap up all the detail that contain the material in this Google Drive that you saw on your screen, that you're seeing on your screen, okay? And it's a continuation from the detail that we explained from the last clip. Okay, from the last clip, okay, we did talk about how do we apply uh, what we call the distributed computing approach, okay, to use in Radic R. Okay, and certainly, I might recall that there are three main parts of the solution. The first part is this program, okay, the big data FFT construction .m, okay, it took a while to load in for Google document here. Okay, here it comes. Okay, and we did set up a test problem with the power of 2 in the unit of 1000 million data. Okay, and we separate into 8 parallel track. Okay, and therefore we can generate, okay, the 8 file contain the data in the format of this one, xrn, xrn plus 1, xrn plus 2, and up to xrn plus 7. Okay, so there are 8 tracks start reference from 0 to 7. And as you can see that it's an open file, and then we just generate the data and then keep writing it down. Okay, and you know that to write the data down, we cannot just utilize or generate the whole data at the same time, because it's the problem of the big data long stream here, that the main memory of your computer is not supposed to be handled. Okay, the second part, as you might recall, is an 8 parallel track of this test big FFT, start from 1 to 8. And if you have 9 or 10 or 11, you have to extend it yourself. Okay, this one is you already saw last time from the MATLAB. Okay, the same one. You need to open the file once you that you created. This one is F1, and then this file you just keep doing FFT. Okay, and then write it down to the real part in FWR1 and FWIM1. And we did this for F1 to F8. Okay, and also we have an output storage file of FWR1 to the WR8 and FWIM1 to FWIM8. Okay, that's the second part, and the final part belong to this file, okay, of big data FFT processing 2 or 3. Okay, not this one, sorry. This one we talked today, but this one, big data FFT processing 2 and 3. This one again is designed for 3 expand for R parallel and distributed computing, that we again you change this line j is equal to 1, and then okay, you forgot, and just keep change this output file of 1. Okay, change to 2, 3, 4, 5 up to the R value for each of this part. Okay, you might recall from radic R. Okay, first we separate x, okay, into 8 files, and then the second part of test FFT one is this. If you might remember last file, or this one, the test FFT here, big data FFT here is what we are doing, the fast Fourier transform for each of these summation, or each of these summation for each m. Okay, for each m we doing this one. And then the third part of the program is that when we apply here the big data processing 2 or 3, 2 become j is equal to 2, 3 become j is equal to 2. Okay, in this one you can start with 1, 2, 3, 4, 5, 6, 7. Okay, and up to the 8 value. Okay, okay, and then just remember that you just have to need to change this one from 1 to 8 or 1 to R according to what the R value that you being designed. This third part is the part that will compute for each L here, okay, for all K, okay, they will, and K is N divided by R element, okay, for each of this subsection, they will computing X for each L, okay, and for each L, okay, based on this formula. And then when L is 0, it's certainly the first equation that you saw on the screen here. And L is equal to 1, 2, 3, or 4. And for each of these, okay, the storage will be keeping the real part. That's the output part, okay, for the fast Fourier transform for FWRS1. This one is omega domain of real part, okay, solution S1, 1, 2, 2. So you just change this 1, 2, 3, 4 up to the R value. In this case, R is equal to 8, and this J also. Okay, so that's the way of the distributed computing environment have been designed. Okay, but today we're gonna talk something about there's some other alternative. Okay, to instead of designing those parallel, okay, to three part of execution. Okay, actually, I prepare other alternative here. Is the sub software we call what we call test big FFT processing. This part, okay, test big FFT processing. We wait a little bit because my okay, this one. This one is just combine the second step and the third part all together within one file. This one I reduce the problem by half size. You need to change n to be the same number as it. Okay. What did I just tell you? I mean that I just erase the parallel step of test big FFT1 to FFT8 or FFTR with any R that you decide. Okay. And I combine it with big data FFT processing tool here. Instead of have a three stage of computation, okay, I reduce it into only two steps. Okay, so that the file of this one test big FFT processing. Okay, actually I already installed all of this into the MATLAB code, and then we will demonstrate. But I'm not going to run it for you. I already run it for you, and we show you a certain of results. Okay, and you can see that this file. This is what this file doing. Okay. Okay, there's a n you have to use the same, and r is 8 again. Okay, and first couple of lines is exactly the same as the previous program. The a, the complex of w, okay, and with the a value, okay, and start to count the time tick here. First, they open the file f1 first, and then you can see that this file they will do FFT immediately here. Okay, you remember that we didn't open F1 in big data FF. If you go back and take a look at the big data FF processing tool here, okay, we didn't, we don't need to open, oh, sorry. You can see that we, once we be able to identify W, okay, we start with J is equal to 1. We do TikTok, and then you can see that we open the file FWR1 immediately. Okay, and then we use FWIM1 immediately also. Okay, because this is all, if you might recall, is in the file called test big FFT M1. Okay, I'm gonna switch around a little bit, so it's gonna take some time because we are doing FFT here, okay? And then once the output be able to identify for each of the specific data segment, okay, this one was first segment F1, that the data been keeping in the file F1. Okay, we are doing FFT down here, okay, and then we save the results, okay, into a file we call FWR1, FWIM1, okay? And that's why when you using the code of big data FFT processing tool, you need to open the file, okay? You need to open the file here, FWR1 and FWIM1. And then you need to merge the results here, okay? Okay, merge once you merge the results, okay, this become a complex number. You create unnecessary variable to reserve more space. So this is what you're doing with big data FFT two, and you can extend it for j equal to 2, 3, 4, 5 up until the last number where the r gonna be. Okay, but for the test data, okay, for this data, test big data, a big FFT processing here. Okay, there's big data FFT processing here. Okay, so maybe you don't forget that you need to change this to be the same size as the construction, big FFT construction. In this one, we just didn't, we would do FFT here immediately, and we're not gonna uh, save this result anywhere using the secondary storage. We perform FFT here. And certainly now J you can change to 2, 3, 4, 5 also. But this one we open, we do FFT here. And then we go to the loop here. And within the loop here, you can see that we just call the file, okay? And for each of them, we are doing FFT again. So FWR, okay, become FFT of the retrieving data for each specific file. And it change over the year. You can see that FWR, okay, change every I that change, okay. So when I is equal to 2, this one is affecting. It's become the second segment of the data, okay, that we decompose it. When I is equal to 3, become the third and fourth, and until, in this case, 8, okay. And then once you be able to FWR here, okay, and you know what is WR here, okay, you can use this. This is the same loop of data, okay, this is the same. The TikToks over here is the same. You can update and find the cumulative, which actually this one you know that we find is execute this one. Okay, this is a command to execute this one. Okay, and certainly execute this. Start L is equal to 0 is equivalent to J is equal to 1. L is equal to 1 corresponding with J is equal to 2 up to L is equal to R minus 1, which is the same as J is equal to R. Okay, so you can see that the program of test big data processing here, okay, working almost similar to big data processing here. But instead of you have to do the second step, okay, okay, instead of you have to do the second step here, that you need to this one FWR1, FWIM1, or to until FWIM. You will see that all of them, you see, when I is equal to 2, you retrieve the second file, the second data segment, third segment, and so on. Instead of, you need to run FFT before and store within this, we just, for the program that uh, we redesigned for this one, test big FFT processing here, okay, that you saw, that you are seeing here, okay, you can see that they just compute it here within this one. Okay, we just compute it here. And then utilize the repetitive data that we didn't like for I is equal to 1, we didn't store the data in one available space, and then the different space allocation for I equal to 2. We store the same, which is FWR, because FWR will be using in this formula. This one you can see that it's the same as a big data processing tool. Okay, but so WR is just compute immediately from F1 here, and FWR computing immediately from F2, F3. And you can see that we can get this summation of this for each loop, and then with this multiplication of W, okay, with summation M equal to 0 to R minus 1, this one, of W to the M, and with the bracket K plus N times L divided by R here, is implemented over here, okay, within the loop here, okay. This is for all the K value, okay, but we changing, okay, for the second round become I is equal to 2, 3, 3, 2, 4, which is It's just a move around from one summation to the next summation to compute the whole, two summation that uh, nested each other here. Okay, so this is the difference that we are doing here. Okay, and I think I have some basic result if you might observe the behavior of this program. Okay, they start with j is equal to 1. Okay, in this one we just run. You can see that we measure the time first. This is the time to compute FFT WR. So it includes the time that you read the data from the secondary storage, okay, that you've been stored under the name of F1, and then the time that plus the time that you execute the FFT, okay, and then for each of these loop after this you get this one. You start to measure up ticks and this depend on I. Okay, for each of this part of tick and top that measure the time here. Okay, it depends on the I value. It just compute the computation of FFT for each data segment. Okay, and that FFT for each data segment is here, over here, this summation, or each of these summation for each M. Okay, for each M. Okay, they will compute this summation. Okay, for to the to get the result that been installed in FWR. Okay, and after that, okay, you are computing what we call the cumulative summation here. So this loop is used to compute this summation here. Okay, summation of the when you get sum of the subpart of fast Fourier transform for each subpart. Okay, of n for m. Okay, because you need to find summation for m. For each of the m you get one FFT results. Okay, and you need to multiply this, and then you need to find the cumulative value of from m equal to 0 to r minus 1. This is what the loop here, okay, is doing for you. Okay, okay, the whole loop here. Okay, start is all start here. Okay, so they're going to measure the time for F1, and then for R equal to 2R, okay, there will be two measure of time. Okay, one to compute the FFT for each part. You remember that this come to replace with the big data processing, that instead of you have a separate file that compute the FFT and then only one, and then you just move it, put it in the file. Okay, so the previous approach that we discussed on the last clip is that we only perform FFT once, and then we put it in the secondary storage so that we can call in and call out, call in and put it back and call the new result coming in. But this one, okay, the disadvantage of this one may be that we need to compute every J FFT of F1 need to be computed, and also FFT of all the file need to recompute for every J when you change the new file to J equal to 2 to 3 to 4. Okay, and certainly once you get the results here, you put the results in FWR. If is a first, when J is equal to 1, you get 1. J is equal to 2, you put this 2 up to the R value. In this case, R is equal to 8. Okay, so you see the difference. The next step, the test data, this program. Okay, you don't need for the previous approach, you need to run big data FFT construction, and then you need to run test big FFT 1 2 3 4 5 6 7 up to 8. In this case, R is equal to 8 in parallel, independent from each other. And then you need to, next step is to run big data processing 2 and changing the J from 1 to 1 2 3 4 5 6, and change the reference file to the same as a J value. Okay, that's the previous approach from the last script. But in this script, you just use the alternative ways. You use big data FFT construction once, okay, and then you using this file immediately. This is only one file, because once you use this, okay, you have to use this file R times, okay, by changing the J. Okay, J is equal 1, 2, 3, 4, 5 to R, okay? And then you again you change the output file here from FWR1, FWIM1 to FWR to FWIM2 for corresponding to each J up to the R value, okay? So before you can do the experiment and make a comparison here, you might take a look in advance or analyze in advance what is the advantage or disadvantage of both approach. Okay, the first approach that we talked about that we discussed in the last clip, okay, have an advantage is because you're gonna compute FFT for the each data subsection only once, and you store it in the secondary storage. But in this integrated software for that you for today's in this clip approach, okay, every time you run it for each the FFT need to be recompute. Okay, they open the file need to be recompute again and again. Okay, the question is that is this cause a lot of effect? As you may see in from the two clip once we start the clip they're talking about the MATLAB uh, platform they're using the Excel that they can go up to 1 million unit and it took less than a minute. Okay. Maybe in this case, if the sub problem here, if for example you have 1,000 unit in the power, 1,000 million unit in power of two, you just for each part you separate in 8 part. For each part is only 100 something million. Maybe your machine just can comfortably solve the 100 million point problem. So even they rerun it again, this might not cause much problem. Okay, as you might see in the previous that computation that the time that you generate the data and the time that you're gonna consume during the retrieving the data from secondary storage and restore the data to the secondary storage sometimes take a much longer time because don't remember you have to remember that FFT is all executed in the main memory that you have. Okay, so so that's what we analyze the procedure that the first procedure that we talked on the last clip have an advantage that FFT compute only once, okay, and you store in the secondary storage. But today's approach, the approach in this file test big data FFT is that every time you run for J, the FFT need to be recompute again and again. But you don't but it's trade off to the time that you don't need to open the output file and then read it and then combine it as a complex number because you open the file the original time domain file and then recompute this again. Okay, so and that's come to the last assignment for all of you. Okay, you have to be careful and study all along from the last clip, okay, the detail of the last clip until today's clip, okay, because in the last clip we talk about the distributed computing approach, the almost fully distributed, but in this one is this approach is also the distributed because it's distributed here because you can run it 8 times or if you have 8 machines in parallel you change this j equal 1 j equal 2 3 4 5 6 7 8, okay, and then you run it every time and then you get this one and change the output here you're gonna get the same output here, okay, but the key issue is that which procedure is more efficient than the other. Okay, that's the final question of the last take home assignment and exam, okay, for you to finish. Okay, so you have to study both approach very well. I give you a little bit for example because the example of using test big data processing .m, okay, I only run it, okay, and I show you some picture of the output run because we correct the data down here, okay. The first data here in left tab is a computation of the finding the FFT of the first from file F1, this one 44.25. And then you can see that there's a pair of data, 50 second, 150 second, 40 second, 155, 34, 154, 33, 150. You can see how many pair. This one, sorry. This one, two pair, three, four, five, six, and seven. Okay, this is seven pair. You get why seven pair, and then the eight is here. You can go back and look at the software, okay, and the file FFT here. Okay, I rather look in this one because in MATLAB you cannot expand the size easily like we doing in here. Okay, you can see that the first one is here. Okay, the first data is TikTok here, and then another seven pair of data. Okay, you can see is coming from here because 2 2 3 4 5 6 7 8. There's exists seven round of this loop. For each loop, there are two number being collect the time consumed. The first one is here. The first one is reading the data, the original time data file for each data segment, and find the fast Fourier transform corresponding to the fast Fourier transform according to those data. And then, so the first one is use this one, top, and the second one is stick and top here. Okay, this one is the way that you compute the whole finishing here. Okay, so the first one is a computation is here. The first one is a computation here. The second one is a computation of this summation to according to the m value. Okay, I'm not sure that you be with me or not. Let's just say that the first value is a computation of this summation. Okay, and then after that you go to the seventh loop. Okay, from 2 to r, trying to find another cumulative here. Okay, that cumulative of this function. Okay, for every round. Okay, for the first round you need this all for j equal 1 to m. For it means for each m. Okay, you get this one. You need a fast Fourier transform, and then once you get this fast Fourier transform, you need to have that fast Fourier transform to multiply with this, and then accumulate with the original start from m from 0 to r. And that's what this output really means. Okay, according to the file of test FFT. Okay, so remember that this is an example of run. Once you use this file, the test big FFT processing here. Okay, quite slow. Okay, when we run this program, okay, step by step, this is we get the results. Okay, and this is based on the problem of 1,000 million unit. On this one is on my computer at the office, so it's a little bit faster than the computer that I'm using here in my home. Okay, so the first one is only 44 seconds. Remember, the size of the problem is around 100,000, 100 million point as a power of 2 in the unit. Okay, so it took only once you separate those data to 8 pieces. Okay, 8 segments. Okay, so each of them is probably around 100 something, 100 million point. Okay, 100 no 120 million point, something like that. 12 8 more than that, around 125 million point. Let's just say that actually it's around 100, almost 130 million point. Okay, uh, and then if you know that, so this one is only take 44 seconds to find the fast Fourier transform of the size, the size of or more than 100 million point. So it's pretty fast, less than 1 minute. And you can see that the 50 is for the second one, for F2. This one for F1, this one for F2. It includes the time that you read the data from your secondary storage, and then you execute the FFT. Okay, so you can see they quite pretty consistent. This one 44 seconds, the second one took 50 seconds, the third one took 44 seconds, and the fifth one took 34, 33, 32, 27, 24. Okay, until this. You might wonder that it's the same size of the problem. Why the response is changing? This one 44, this one 50, and then start reducing now to 42, 34, 33, 32, 27, 24. That's because this is a commercial software. the commercial software invests a lot of research to improve efficiency. If you're using MATLAB several times, you would find that if you have a certain problem that you run, this is just my own experience. The first time of running probably took long time. This one you can see that this is the individual one 44 seconds. But when you get this the second 150, you get into the loop. The first one it took long time 44 50. But then in the second loop, okay, when j is equal to this j is equal, this is the first loop that compute the FFT of F1. For j equal to r2 to r for I, sorry, for I equal in the loop of the program. This one took 50, okay, and then for 20, 42, 34, 33, 32, 27, 24. It keep improving, iteration by iteration. You know, it means that the software have been designed to have some, some special thing, learning process. In today's world, we can call this a machine learning. Okay, so they did have some AI. That's what my personal belief. We did the software that if you keep running to solve the same problem, okay, similar problem, they have some adaptive algorithm to speeding up. If your main memory and your CPU is still work in the comfort zone, it's not unresponsive zone. Just like and you know that when you increase the size of data even more, this thing is not gonna happen. So it's mean that with my, in this case, with my 1,000 million unit plus something in the unit of power of two, okay, it's possible, okay, to run it in real time here. So what is the second value here? Like 149, 155, 154, 159, 160, 158, and then one. This is pretty consistent. Actually, it's the execution of this one to get the resolved data segment when L is equal to 0. In this case, J is equal to 1. Okay, to finish this. And then the last one, the last result here, the 11 second is what? It belong to the last unit of time collect data collection for time collection here. You can see that toward the end, okay, after you finish the loop here, okay, okay, when you finish all this, you get the new one. You start counting the time again. This one you open the file, the output file. For the first segment, it's like this one. In this file, it belong to L is equal to 0. Okay, you get FWR1 and FWIM1. Again, this problem is also very easy to run, just similar to what you did with big data processing. And when you change to 2, okay, you change to 2. Once you change to 2, this one no change, no change. The loop here is no change. You can this one keep constant, okay. Just change the final one, change this to 2, FWIM2, 3, 4 up to the R, in this case the 8 value. Okay? So that's just I wraps up this program of test big FFT processing here. Sorry. That's the two approach. Both have a distributed computing approach. Why distributed computing? Because we be able to look down at the way to process the formula here of the radix R, that you can at one point you can separate the independent run. Okay, like in the case that you can start from j equal 1 to 1. Suppose you have a 4 computer run simultaneously. You have to, you can run it in parallel. You don't need to wait anything. Okay, and uh, but in your case, we're gonna talk about that. If you have only one computer in yourself, you have to act like okay, you have to start to run one at a time. Just like in this one for the resource here that I show you, okay, over here. Okay, this is just run for j is equal to 1. Okay, for j. You need to go when j is equal to 2, when you using this one, the test big data FFT, j is equal to 3, 4, 5, 6, 7, 8. Okay. So the second approach, okay, the first approach I talked to from last script, and then earlier this script I did repeat it. But for the second approach, okay, in summary, you start using this one first, okay, this file, big data FFT, to generate 8 file here in terms of, and then you using this test big FFT processing, okay. Again, you as you see, as I showed you before, change J from 1 to R, and then for each J the change, okay, you just change the output file FWR1 2 3 4 to R value, okay. And your final take home exam is that once you run and you get the result, okay, first of all, okay, you collect the result from each on your computer, and then you write a report, okay. You might use the same notebook as you did from the take home exam according to the partial differential equation and ordinary differential equation that we discussed before in the clip before. You can use the same notebook, but you have to write it by your hand, writing your hand, okay. Do not type. I don't believe in your typing. Just write it down. Write what you see from the results, and then you need to analyze, and with some now I have two tools for you: the approach to solve a specific problem, okay. And the specific problem is that uh, do I have to do we need to use this a million uh, no 1,000 million point? The question is no, okay. I I just assume it to you here now, okay. For the big data construction here, okay, let's start, okay, for the final exam problem, okay. uh, let's raise this problem to, okay, let's say 2,500 million point. We remember that. Let's escalate this to 2,500 million point, okay. 2,000. Last time we talked about 2,000 million, right? But I forgot to say 2,500 million point is the target for your final exam, okay. And then you run it by both approach, okay. Once you run it by both approach, you can see that you can observe the processing time for using each approach by using the tick-tock command, okay. Get the results of elapsed time for each step that the first approach used, and for the second approach is collect here. This one just for one J. Once you change another J, you get here. And then you make a conclusion analysis that which approach you think that is a better one and why, okay. And then analyze the result of your running program and write your decision, your final decision based on the analysis of the output performance here, okay. And that's the final take home exam, okay. And we're gonna go to this, that we have another program that you might be interesting here is this program is called Big Data FFT Processing.m. I didn't run this program. Actually, this program is a program that wraps it up all the things that we done within just this program. You can see that this program, we start with the clear memory, we start with the NS of 100 million unit here. All the view is the same. But you remember that each time we need to change J from 1 to R. This one we just add another loop here. Okay, I'm gonna run J is equal 1 to R. Okay, and the rest is using the test. The rest here, okay, for each loop of J, we doing this the thing that's the same as what we are doing with this file of test big data, big FFT processing here. So for each J, so very easy that we, instead of we change the J equal 1 to R, you can run separately. We combine this all in one, in in this program. So the file big data FFT processing.m here is kind of all in one. Okay. Now you don't need to have a parallel or distributing anymore. Everything run in sequential. For j is equal to run, they're gonna open the file, find the FFT, and then we go. But I don't suggest you to use this approach because it might turn, especially for the problem size of even the 1,000 million, and it took a long time. But if you don't believe me, you can do it. It's just, but this is just actually the origin should start with this program, but we didn't have much time to do that in this course. So I just give this for you as a gift at the end. That this is the only one instead of running a several program, this one all in one within this program. But the disadvantage of using this program is that everything is in sequential mode here. Like J is at J equal to 1 to 2 to 3 to 4 to R. So it's gonna take a lot of time before you get all the results here. Because you can see that toward the end here, okay, when you open the file, okay, when I is equal to some case, they open different file. And also toward the end, when J is equal to 1, you instead of you need to open this one, you can see that when you separate the program, you can say j is equal to 1, you just put this. When j is equal to 2, you put this. You have separate file. But in this one, when you move it up to the same, move it all in the same program, to at the end, you need to use the file when consider for each possible j value also. Okay? Hope you understand that actually this program as a big data FFT processing here is just combining all the distributed idea that we give you in the first place into all in one. When it's all in one, it's look to be a very nice idea. Okay, but it's not the nice as you think you're going to be, because if you don't have your many computer in parallel, you cannot execute it. So that's why you can see that this is a basic sequential processing of the approach. Okay, but the other two approach we discussed before, at least that we try to utilize wherever you can process the results sub solution in parallel. Okay, and we also add one more program for you. We call check solution FFT.m. Okay, this one is a program that you can check all the approach that you are doing with a small scale problem. Okay, as you might remember that when n is very large, okay, your results over here, okay, you can see that this is n is equal to 8,192. They're gonna do the same here. Okay, they're gonna do x here, separate into r in parallel, and xt is the original in the time series, because remember that this one can test only small data. Okay, and once you get the small data here, okay, look at what we are doing here. Okay, uh okay, first of all, okay, we open the data according to the original x area. You remember that this is what we did, that we separate the problem into the r location to have an r location lag that, so that it fit with the formula of radix r here. Okay, and then we open the file here. Okay, okay, for each of them, okay, for each of these x, okay, and then this is what we are doing is that, okay, we link the data, okay, for xij to xtix. Okay, xt is a original long string one dimension of the data. In this case, it contains the n. For I think that for the 8,192 data. But for each of these x, okay, for xt is a long stream, 8,192. But for x, it becomes the matrix. So dividing this data to 8 segments, okay. And each segment is only 1,000. You can find the division. It's only 1,024. Okay. For each 1,024, store it in the file f1, f2, ft up to f8. Okay, and then you, in this case, since the n is not very large, so you can, this is what you can do. you can, you see that? You can find the FFT immediately, okay? And once you find the FFT here, okay, in this one, okay, it's a file that you're gonna open up here, okay? You you have to know that we assume that before running the check here, okay, you already run this file, the construction here, okay, the file, which means that the file F1 to FS has already been built, okay, and then for the check program, okay, you reopen it again, but open to read the results, okay. This is the time domain results because when the data already separate, so when you read it, you need to put it back in the form of the matrix here first, and then you just transport the data of X here into one long stream of XT, so that once you know XT, you can find the FFT of XT. And then if you already run both approach that we talked previously before, at the end you're gonna get the result of FWR1, FWRIM1, FWR2, FWIM2, and so on, okay, over here, okay. And then for each of them, okay, this is the output results, okay, real part, imaginary part. You just take it back, the real part, put it back in vector A, the imaginary part, take it back to imaginary B, okay. And then you get FW1. This is the first segment of the output data, okay. The fast Fourier transform. The segment is a complex. Add A and B as a complex number. And then you get FW2 also as a resulting up to FW8 and in the final one. Okay. And what did I do next? Okay. Now you can see that you have the results here. XW, okay, is the result of the direct fast Fourier transform, which for the you can test for a small problem, okay. But if you already have test with a small problem, you just put these results, okay, try to run both approach again with this small n, and then you once you get the results here of FWR1, FWIM1 up to FW, and in this case, what if we still contain the S segment of data, if FWR8 to FWIM8, now you get the result of FW1 to FW8. If you merge all the result of FW1 to FW8, the result should be close or at least approximately equal to XW. Okay, so this one is a kind of find that can help you to check whether did the approach that you are doing get the correct solution for small scale problem. Because in large scale, you already know that you can't find the FFT. So you can only check this with the small scale problem. Okay. So that actually this program should be doing with both approach in the first place, so that you can make sure that when you extend for the larger size problem, it's gonna be able to run. Okay, and give you a correct result. Okay, so this is a further part to help you to check the results. Okay, and I think that like test FFT Excel over here. Yeah, this is another file. You might take a look and try to cover all the detail. This one is, as you already know, that you can find the Excel. This is just like what any other program that we already do. You can import the data file from Excel and then you just use the direct FFT. Okay, and we already explained the results here. This is the Excel file for the test problem. Okay, and this is a file, the complex number here. This is just a demonstration file that help you that why the command of complex just combine. Okay, combine the A as a real part and B as an imaginary part. You can use complex AB and then they will give you a complex vector down here, C, D, E, F here. Okay, and then you can manipulate. After that, you can manipulate the complex operation, yeah, immediately. Okay, remember that C transpose in if you have a complex number, is become complex conjugate. Okay, which means that the once is transposed, the imaginary part need to be the negative, the opposite side, as the once is not transposed. Okay, for example, if you have some value of 1 plus I, if you transpose it, okay, instead of that row become the column, it become 1 minus I. Okay, that's the thing that you have to know, that for complex operation. Okay, that's about it. All the program has been explained, okay, in this clip. Okay, so you should be able to run it. Okay, all the problem has been assigned and has been talking about for you. Okay. Okay, I think that there's still one more program left that I didn't talk about. Okay, is this two program there. FFT decomposed it. Okay. Okay. Uh, Actually, this is the idea that you start with a small one, also this one, and then you find the direct FFT results, and then this one you get the decomposed method. Okay, this is also the serial. Is similar to what you are doing with the all-in-one program like this one in the big data FFT process. But big data FFT processing here, you already make sure that the data is so large that it's been using the second storage. But for the FFT decomposing, you assume that all the data can be executed in the main memory. The first part here is just direct FFT, okay, FFT. Get the data FT in time domain, and then you get the frequency domain result in FW. Okay, the second part is here. Okay, you separate the result to separate the original data to R segment. Okay, and then you start okay, allocate each R segment, but you don't need to store this in the secondary storage. You can applying FFT for each part immediately here. This one you FFT for each column J. Okay, okay, and put it in FWR. Okay, that already get the what we call the complex number results. Okay, and after that you just put it in here. You get all the results, and then you just, this one is pretty similar. They doing this, and then you get the result in FWS here. Okay, so this one is all in one using the main memory, purely using the main memory. The limitation of here is that as n increase, it's gonna stuck some with some n value. But as you will see that it can go up to a million unit, okay, multi-million unit, even 100 million unit, as we show you. But when it reach the to around 1,000 million unit, we're gonna get stuck. As you saw from last example, that when you move up to 200 million, you cannot run. But remember that our homework assignment, we expect you to try to solve it at the size of 25,000 million. Okay, and compare both approach that we talked about in the last script and today's script earlier. Okay, and for each of them, you're gonna get the collection time of processing for each part of the program. Like for the test big FFT here, okay, you can see that I already put the TikTok command for you over here also. You can see that you can have here. They will have TikTok command when you're doing the FFT. Once you read the data, this one, this is a time consumed when you read the data for each F1 or 2, for each data segment, and then the second part is a processing time for perform just pure FFT, and the third value is that the time that you restore it in the secondary storage. Okay, so all data collection here has been put in all procedure that we've been talking about. You just collect the time consumed. Okay, and don't forget that you have to make sure that why you think that the program is correct by using the check solution FFT to to check whether the solution is correct or not. Okay, and uh, Actually, FFT decompose just give you, you don't need to use this. Okay, this one just direct main memory utilization. And or if you want to do, you might try to say that with this approach, how far they can go. If you just don't use any secondary storage at all. Okay. And the last program in this section we call FFT Fuller Series. Okay. I think we should talk this a little bit, even though it's not related much to the final exam. Okay. But at least it has a this program provide you a linkage to what we call, okay, I'm gonna increase the size here. This one is okay. Yeah. This is a very short program to show you a little bit of the relationship of Fourier series. As you can see that from the original paper of Kuri and Tukey, they didn't even mention the name fast Fourier transform. They just talk about I'm going to develop an algorithm to find the coefficient of Fourier series. But as you see from the original discrete Fourier transform here, for the Fourier transform formula, it's not Fourier series, it's an integral. But once you discretize the continuous mode of Fourier transform to discrete Fourier transform in this form. Okay, this approximation closely related with the Fourier series. Okay, why is closely related? This program is an explanation. I'll explain to you a little bit. It start with the clear memory. Suppose that we have 50 data. Okay, and FT is a time series domain of 50 data. And we generate FT based on this random function. And then once you find the FFT here, you execute the FFT, you get FW as a complex number based on the formula. And then you separate FWR, FWIM. Only take the real part and imaginary part of the complex vector FW. Separate into. Okay, when you use complex command to combine them, right? And when you have two real number, you want to combine it as a complex number. And then the same as that you use the real command and y minus imaginary, y minus value of imaginary, because of the original formula of discrete Fourier transform here is e to the minus I 2 pi. You can see that the minus sign here dictate the what the program gonna look like here. Okay, minus. And then this one is a FTC is a Fourier series coefficients. Okay, FTC here. Okay, and this is a function that, okay, no, this is the you want to compute the original FT here. Okay, this is FTCC coming from comparison. I'm gonna compute FTC again. Okay, by using sorry, we shouldn't do that. Okay, okay, we this is what we have to do. We do FTC, okay, equal, oh sorry, then FTC, no, FTC equal to, we call 0, no, 0 n1. Okay, this original is here. Okay, but you can see that this FTC is computing here is cumulative of this FTCI plus FWR. This is the coefficient FWR time cost of 2 pi j minus 1 time I minus 1 divided by m, and FWI time psi here. Actually, this is what does this function do? This function execute this of Fourier series. But it become what we call the truncated Fourier series, because n is equal to 1. Instead of going to infinity, which means you run it, you're gonna go forever. It have a finite approximation here. This is a finite approximation of the code here. The n is a finite approximation here. The 50 term of the first 50 term of Fourier series. This is cos pi divided by n. Okay, this one you, as you might remember from the formula of Fourier series, is become cos 2 pi, okay, 2n pi t divided by t. As you know that t is a number of is n delta. Okay, this the above here n here, and t the above here is become the running by the for this code is running by the I value, okay, and the j value is running the t, okay, but t is the delta j, delta slightly delta, so divided by n, okay, and n, this n value, okay, move along with the I value. So but you have to know that this one start from a0, the index here, so that's why the index of j and I need to be reduced by 1. Okay, so this is cos 2 pi nt divided by capital T. This is sine 2 times n, 2 times n prime time t divided by capital T also. And you be using FWR and FWIM. Where do you get this? This is the real the real data and then the imaginary data from the result of FFT. And it means that the resulting of FFT, the real part, is corresponding to the this value. And that frequency is 0. Okay, this one is A0 divided. So the coefficient of the real part rely on the cos term and the constant term. And the coefficient for the imaginary part rely on the sine term. Why? Because as you might recall that is here. The real part is the cos 2 pi times n. The imaginary part is minus sine 2 pi times n. Okay. Yeah. But when you have this, okay, and then when you use this approximation w to the nk n times k, okay, you add this n and k all together here, and that's what we did with this program. So in conclusion, there is that the relationship between Fourier series and Fourier transform is that the resulting of Fourier transform, the real part is representing uh, in the Fourier series representing the constant term and the coefficient that multiply the cos term. The minus imaginary part represent the coefficient of the sine term in Fourier series. And that Fourier series is not running from 1 to infinity. It was discretized to only n term according uh, only n term. Okay, so a lot of time we call this as when n, actually it should be capital N, okay, because n here and n here, I'm using the same n, but this one should be the maximum of n in this one. N is equal to the maximum of n here, okay, and this when you approximate it with some finite summation here instead of infinity, we call this a truncated Fourier series. It means that the Fourier series we approximate with a finite sum, okay, and as long as this finite sum keep increasing the number of terms, the approximation of ft to the original is getting close, okay. So that's what the relationship that we, that's why the original paper of Kuri and Tuki talk about we are still working on the Fourier series coefficient, okay, and it can be illustrated by using this program. If you are interested, you go and run it and study it, okay, but it's not talking, it's not dealing with anything in final exam, but just to find this is a big linkage, as you know that the general solution for the partial differential equation is in the Fourier series form, most of them, okay. Therefore, and to be able to establish the coefficients that multiply, okay, that multiply each term in Fourier series. And if you can approximate it, why you want to approximate it? Because a lot of time your f, you can go back and in the classical Fourier series here, to be able to find this coefficient, your f of t must be integrable, or even when you multiply by cos of sine term, this function, the resulting function, it must be integrable. Integrable is mean that you need to find a finite and well-established closed form coming up. But a lot of time with the given input of f of t, suppose when you collect it from some IoT, the sensor in the real world, where you sense the data in time domain here, you cannot expect that you're gonna get a well-defined function t that's integrable anyway. Okay, sometimes you get a series of data with resolution. Okay, that you eventually need to use Fourier transform to approximate it anyway. So it means that when you get an approximate time series data for continuous data that found in the time series that you want to analyze it using a Fourier series to get the coefficient here, you can use all the methodology that we study about Fourier fast Fourier transform to help you to find that representation. Okay, and this is just a pure large basic knowledge about the relationship of Fourier transform and Fourier series. And Fourier series, you already know that Fourier series have some big relationship with uh, many of the partial differential equation. Okay, application. Okay, but again, okay, for the MATLAB part, okay, we studied two approach of distributed system, distributed computing approach, okay. To solve, we expect that you to solve a large scale problem of the size. You want to find the fast Fourier transform of the size, again, 2,500 million point, okay. And then once you collect the data of time, computation time for each step of that two approach, okay, you analyze it and make a conclusion that for me that you think which approach is better, or on some aspect this approach is better, why, on some aspect this approach is better, why. But for, and then you make a conclusion that for the 2,500 million point, if you can recommend the approach to solve the problem, which of the two that you will select and why. Write down clearly with some illustration and not just dreaming and write it down. You have to run it and get all the results and analyze those results to support your claim. Okay, and that would be this one. Okay, for the Fourier fast Fourier transform. Okay, remember that there's two data, two problem. Okay, the problem that you need to submit is that on the Excel, okay, that contain in the file of FFT big data. Okay, we talk about this during the clip that talk about the Excel platform. There are two size problem. The first size of the problem is that this one, 65,000 65,536. Okay, it took a while for me to download it. Okay, this one. Okay, the data just start to coming out. Okay, to like this one. Okay, you get finishing as 65,536. Okay, but remember that we in the file of Excel here, okay, on page 3, I'm not going to open it, took some time. You go back on sheet 3, okay. There's some command that you can keep generating the data for a larger size, and the size that we are looking for is what? You might recall again, okay, and the size that we are looking for, okay, is what? 3 times 3 times 8,192. Okay, no, not 6,000, it have to be 8,000. Now today I'm doing on Google Sheet. Okay, so this is the second size problem is 73,728. But you can see that now it's become 8,192. And previously we show you that you can solve, you can extend from the maximum size of 4,096, remember that, to 8,192. Okay, and it show you in this file, okay, for FFT. And also we also have the file of Excel FFT 16,384 that show you that once you be able to get 8,192, you can get this one also. Okay. And the last one is that there is a sub sheet in FFT big data that we illustrate you how to apply the radix tree for small scale problem. Okay. And I already conclude that that should be enough for you to apply to solve this problem of this size. Okay, because you need to apply radix tree uh, into layers. Okay, so it means that you're gonna end up, okay, need to generate each part of the first one is that you can see that if this is coming from the formula tree, but you need to solve a subsystem of 8192 and doing radix tree first. Okay, this one three times is you have 8192, okay, separate into 9 part, okay, to 9 part. You can see that it's separate into 9 part, okay. But the first three, okay, uh no yeah, the first for each, for the first 3 part, okay, okay, this one 8192 you need to separate into 9 part, okay. Okay, like 8192 and then separate to 9 column, okay, and then just keep running the number, okay, 1 to 9, and then 10 to 18, and go on and move row by row until the last row, okay, and then you take data in each column, okay, okay, you can hit, and now you can separate the data into 9 sections. For the first 3 section, okay, okay, of 8192, you need to perform radix tree, okay, and the first, you have 9 sections, right? The first three from section 4 to 6, each of them have a size 8192, perform another radix tree, and the last one from 7 to 9 data section, each contain 8192, perform radix tree. And for each 8192, you already know that you can't compute 8192 FFT immediately. You have to use the idea of solving 8192 from this file FFT big data, which I already showed you from the previous script, okay, to solve 8192 first. You have to do it in, 9 section data, okay. So actually it should be 4096 separate to 18 sector, okay, and combine 8000 4096, okay, to 8192, okay, to 9 segments, and after that three each separate to 3 group, each group contain of 3 data segment, okay, of 8192, okay, and then you use the platform of radix tree, okay. We already show you small scale to get the result from each of this, and then do it radix tree again, okay, for each part that contain data of 3 times 8192, and then you get the result from this size of problem, the 73,728, and then you can check the correctness of the result of both case, okay, of 65,536 with this, okay, by run the result, use the same data file, import the data file to the MATLAB code environment, okay, and then use MATLAB to find the exact solution, and then you can compare whether the process that you do on the Excel give you the correct answer or not in the MATLAB, okay. That's, again, I repeat the question for the math for the Excel environment, and in conclusion with the MATLAB, okay, again, okay, for the MATLAB, okay, we give you a two approach of distributed computing, and what the size problem that I want you to solve is 22,500 million point, okay, and there's two approach, okay, okay, that we already talked about. I'm not going to repeat it again. Two approach of distributed computing system, okay. Analyze the time the computation results, okay, and then make sure that you check both approach, okay, is workable for a small size problem, okay, and then conclude all the result, write all the report of what you are doing, and then give the conclusion that what is the advantage of disadvantage of both approach based on the data that you collect from the computational run. And then for this case a study that I gave you to work on with 25 uh, 2500 million point, which one would you suggest is the appropriate method and why? Okay, that should be it. Okay, I think that I cover all the aspect of the problem. Okay, and we discuss every detail. Okay, collect and all the data that related in and the MATLAB code that attached and all the Excels and what platform, okay, that contain within this Google Drive, okay, it's all been talking about, okay, detail. And also, we didn't have time much to for the related document to talk all of this because this is a small portion part. As I told you, that this subject can be taught the whole semester. If you or if, one day if you want to be an expert on FFT, okay, and all the additional document here can give you a basic foundation. And actually, I missed one thing that I didn't talk about. It is this paper that give you a final one. The solution by fast Fourier transform of Laplace equation. Okay, this will give you an exact relationship that how do you get from fast Fourier transform to Fourier series. That is a general solution for Laplace equation. And this is where it all started. This paper from Campbell way back in the physics world, okay, in 1980, okay. And it's certainly not. It is not going to relate it to your final exam in this course, but many of the idea that we talk about it, if you extend it to study this related document, and when you reach your senior year, if you're still interested to do have some idea to do this, extend this work for your senior project, you can drop by and then talk to me. Okay, give you this is just a last tip. Okay, not only in this course, just that if you are really interested in this topic, you can you go back and read more about this related document here, and then we can setting up some senior project for you to finish. Okay, but if you're not interested, you go and find something else to do with many aspect of industrial engineering that's still valuable for you to practice and to develop your skill to solve it. Okay, and that should wraps up all the detail about this course. Okay, and again, I'm gonna this assignment is due on uh, May 13, right? As we express it, because this is the last day of the exam. Okay, but since this is you have maybe around 10 days left. Okay, for this last assignment. Okay, this last assignment, I'm gonna give you maybe 2 more days. Okay, instead of 13, this one is the last assignment that I'm talking. Uh, but if you want to submit within December 13, that's fine. But if you need more time, okay, I gonna extend it to Sunday, May 15. Okay, so if you think that May 13 is just this one, okay, the assignment, the last assignment that we talked in this script, okay, it can be extended to May 15. But if you prefer to finish within May 13, you're gonna have to work very hard. But it's possible anyway. Okay, so good luck to all of you, and I'm looking forward to see your final results submitted. Okay, I'm gonna put this in the whole assignment, the last assignment, and do and assign to you through to the Google Classroom. Okay, for the final take-home exam for the second part evaluation of your study in the second after the midterm exam. Okay, the all content that we cover here. Okay, so I'm looking forward to see all of your submission, and hopefully that you work hard enough, and then you provide me with the sufficient evidence that you should pass the course. Okay, so looking forward to see in your submission. Okay, see you. Hope to see you in the homework submission. Okay, bye.